Every time you do anything on the internet, log in, send a message, upload a file, your data is transformed. Sometimes to make it travel safely, sometimes to store it compactly, sometimes to protect it forever. 3 different problems, 3 different solutions: encoding, hashing, and encryption. Most people think they're the same thing. They're not. And confusing them is exactly how security bugs get introduced. In this video, we'll build a complete mental model of all 3, starting from the browser URL bar, all the way to how your bank protects your password. Let's start with encoding. Type, "What is encoding?" into Google and watch the URL. Spaces became %20. The question mark became %3f. The browser didn't ask you. It just did it automatically. Why? Because URLs have a strict rule. Only a limited character set is allowed. Letters, digits, and a few symbols like hyphens and underscores. Everything else must be converted. The conversion rule is simple. Take the character, find its ASCII code in hexadecimal, prepend a %sign. Space is hex 20, becomes %20. Question mark is hex 3f, becomes %3f. This is called %encoding or URL encoding. It's reversible. The server decodes %20 back to a space before processing your request. Encoding is never about hiding information. It's about changing the format so it works in a specific context. Now let's look at 3 common encoding formats. Take the word hello. In binary, the language computers actually speak. Hello is 01101000101010101010110110110110110111. Each letter maps to 8 bits using the ASCII standard. That's 5 bytes, 40 ones and zeros for 5 characters. Binary is great for machines, but hard for humans to read. So we invented hexadecimal, base 16, which groups every 4 binary digits into one symbol from 0 to F. Hello in hex 68, 65, 6, C6, C6F. Much shorter. Hex is everywhere. CSS color codes like hashtag 307AFF, memory addresses and debuggers, SHA hashes. But sometimes you need to embed binary data inside text, like putting an image inside an HTML page. That's what base64 is for. It takes binary data and maps every 6 bits to one of 64 printable characters. Hello becomes AGVSBG 8 equals, slightly longer, but now it's safe to put inside JSON, HTML, or an email. Same data, 3 different formats, all reversible. Here's a real example of encoding in code. In CSS you might write, button, background color : hashtag 307AFF. That hex color is just an encoded form of RGB, 48, 122, 255. Same color, different representation. Now for images. Normally you reference an image by URL. img src equals quote https://some-image.png quote. But what if you want to embed the image directly into your HTML with no external request? You convert the image binary to base64 and embed it as a data URI. img src equals quote data image/png base64 ivbrw0kgo quote. The browser decodes it on the fly. The image is the same. It's just been encoded for a different context. The key insight about encoding, it's always reversible. There's always a decode function that gets you back to the original. That reversibility is what separates encoding from hashing. Now hashing. When you sign up to a website and create a password, the website should never store that password. Not in a file. Not in a database. Never. Instead, it runs your password through a hashing algorithm, a mathematical function that converts it into a fixed-length string called a hash. That hash is what gets stored. When you log in, the server hashes what you typed and compares it to the stored hash. They match, you're in. They don't, access denied. Now here's what makes hashing different from encoding. Hashing is irreversible. There is no unhash function. If a hacker steals your database, all they get are hashes, and there's no mathematical path from hash back to password. Second property, deterministic. The same password always produces the same hash. Every single time. On every machine. Without this, login would be impossible. Third property, fixed length. SHA 256 always outputs 256 bits, 64 hex characters, regardless of whether your input was 4 characters or 4 million. These 3 properties are what make hashing perfect for passwords. Encryption is the third concept, and the most powerful. Like encoding, it's reversible. But unlike encoding, You can only reverse it if you have the key. Start with Caesar's cipher. Shift every letter in your message by 3 positions. A becomes D, B becomes E, and so on. I am Batman becomes LDP Edward. To anyone without the key, that's gibberish. To someone who knows the shift is 3, they can reverse it instantly. Modern encryption works the same way in principle, but with mathematically hard problems instead of alphabet shifts. AES, Advanced Encryption Standard, takes your data and a key, runs them through a series of complex mathematical transformations, and produces ciphertext. Without the key, breaking it would take longer than the age of the universe, even with every computer on Earth working together. The key insight: encryption is reversible, but only with the right key. This makes it perfect for protecting data that needs to be read later, like files, messages, and HTTPS traffic. Let's put all 3 together. Encoding, reversible, no key needed, changes format for compatibility. Use it when data needs to travel through a system that has character restrictions, like URLs, emails, or HTML. Hashing, irreversible, no key, one-way transformation. Use it when you need to verify data without ever storing it. Passwords, file integrity checks, digital signatures. Encryption, reversible, requires a key, protects data from everyone without the key. Use it when data needs to be stored or transmitted securely and later recovered. The classic mistake: using encoding where you need encryption. Base64, encoding a password doesn't protect it. Anyone can decode it in 1 line of code. And using hashing where you need encryption means you can never get the original back. Understanding the difference isn't just academic. It's what separates a secure system from a vulnerable one. Thanks for watching. Subscribe if you want more deep dives into how the internet actually works.